Hello everyone. In today's class, we will go through the ice tables. The ice tables are basically used to find for example, the final mole flow rate or the final concentration in terms of initial conditions such as initial concentration, initial molar flow rate, okay, and also with respect to stoichiometry coefficient. So let's do an example. So let's say our reaction is A plus 2B gives us C plus D. Okay, so let's say we have 1 mole of A and 1.5 mole of B. What is our limiting reactant? So basically, which element will run out first? That'll be B, because for 1 mole of A, you need 2 moles of B. And clearly, we don't have enough B, therefore that's our limiting reactant. Therefore, the ice table will be in terms of B. The ice tables can be done in either flow rates, in terms of flow rates, or concentration. So let's go ahead and do an ice table in terms of flow rate. So FB naught. Okay, that's the flow rate of the limiting reactant. So let's draw out our ice table. So S, that's the column for substance, initial, changed or converted, and exit. For the substance, we're basically just listing the elements in our reaction. So it's A, B, C, and D. Oops. C and D. The initials, we're just listing the initial flow rates or the values if we have them. Okay. These two are usually 0 because they're products, they're being produced, so there's no initial flow rates of them. But we'll leave them be. Okay. For the converted, you always want to start with your limiting reactant. So since it's a reactant, it has to be minus initial flow rate times X, which is the conversion rate. So basically, this is how much of B has, or of our limiting reactant has been converted or has been consumed or has been reacted. Okay, we want to do the same thing in terms of A. So what we'll do, we'll use the same limiting reactant, how much has been converted, but we'll times it by the stoichiometry coefficient to convert it in terms of A. Okay, we'll do the same thing for C, but in this case it'll be plus because it's a product being produced. C over B times how much of B has been converted. Same thing for D. Okay. Now for the exiting. For the exiting, we're basically just looking for the moles of A exiting or leaving, or also the final molar flow rates. So that'll be the initial minus the change or the converted. So it's basically FA equals FA naught minus A over B times FB naught X. We'll do the same thing for B. And for C, leave this as a 0. And for D, again, it's plus because it's a product being produced. Okay, and there you have it. That's your final molar flow rates in terms of initial conditions and stoichiometric coefficients. Can this ice table be done in terms of concentration? Absolutely. Let's do one. Let's draw one out. So our limiting reactant, as you remember, it was B. So we'll do it in terms, the ice table will be done in terms of the limiting reactant concentration, which is CB naught. Again, substance, initial, change, and exit. Substance, we're listing our elements in the reaction. Initial is just the values of the initial molar. Oops, we're doing it in terms of concentration. Let me correct that. Ca naught, okay. Cb naught, Cc naught, Cd naught. Usually these two are 0 because we don't have any value for them in the inlets. They're being produced. How much is the change, or how much is being converted? We'll start with our limiting reactant minus Cb naught X. That's how much limiting reactant, concentration of the limiting reactant has been consumed or converted. We'll do the same thing for A, but in this term we'll times it by the stoichiometric coefficient. Okay. For C and D, it'll be plus because it's a product being produced. Let me times it by the stoichiometric coefficient plus C over B. Okay. Right. Now let's find the exiting concentrations. Ca final equals Ca naught minus A over B Cb naught X. Cb final equals Cb naught minus B naught X. This can also be written as Cb naught 1 minus X. Okay. Cc final equals 0 plus C over B. Okay. Same thing for D. Okay, there you have it. Your final concentrations in terms of initial conditions and stoichiometric coefficients. Another thing I want to go over is the reaction rates. So how to convert the reaction rates in terms of another reaction rate. So for example, in a problem statement, if you're giving the reaction rate of C and you want to convert it to the reaction rate of A because all your initial conditions and givens are in terms of A. So how can you do that? You'll basically use this formula here, which states that negative RA over A equals negative RB over B equals RC over C plus RD over D. And we're assuming we have this reaction. Okay, so it's basically the same thing as we done in the ice tables above, taking the stoichiometric coefficients into consideration. So let's say I'm given the rate of reaction of C and I want to convert it to A. So I'll take these two out of the formula and equal them to each other. RC over C. Therefore, I'll cross multiply negative RA equals A over C RC, which is RA equals negative A over C RC. And that's how you relate one reaction rate to another in case it's given in a problem statement in a reaction rate that's not useful. You'll use the stoichiometric coefficient to convert it to the reaction rate you want. Okay, that's it for this class, and see you in the next one.